Okay. Hello, good morning, and good afternoon, and good evening. Welcome again to this World River, the Delta System Source to Sink webinar series. And this is Paul from NC State. This talk series is co-sponsored by NSF, National Science Foundation, NC State University, Louisiana State University, State Key Lab, in Eastern Normal, China University in Shanghai, and Utrecht in Netherlands, and CSDMS. So today, we are very happy to invite Dr. Jon Hawkings from UPenn come here talk about elemental export from the Greenland Ice Sheet to the coastal ocean. So before I introduce Jon, always I mentioned in the past 2 years, almost 2 years, we have already have more than 100 talks, and all of them have been archived on our YouTube channel. So feel free to use them for your research and education. And at the same time, we also have a Source to Sink Twitter account. As you can see, we will announce every week's weekly talk, news, publication, conference. So welcome to follow us. And next week, same time, May 11th, we will have Dr. Thomas Hoffmann from German Federal Institute of Hydrology come here talk about the Holocene and Anthropocene sediment dynamic in the River Virginia. So, so please mark your calendar. So as I mentioned, Jon now assistant professor. He just arrived, he just studied over there at the UPenn, Department of Earth and Environmental Science. And before he come to UPenn, he been a research associate at the University of Bristol, and also some research global action, fellowship in Florida State University, and also a little bit of time in Germany. And so he got his master and PhD from University of Bristol over there, PhD in 2015. His research is mainly focused on the flow of elements through the Earth system, is particularly in the coolest area, in the high latitude. Particularly, he interested in the role of glaciers from mobilization of and export of the bioessential macro and macro nutrients to the downstream environment. So also subglacial biogeochemical weathering process. So I think, Jon, now I'll give a floor to you. Please go ahead and share your screen for the presentation mode.
Perfect. Can you see that okay?
Yeah, good.
Lovely. Okay. Right. Yeah. Thank you so much, Paul, for the introduction and for the invite to speak today. It's a great pleasure to come and speak to you from University of Pennsylvania in Philadelphia. I've only been here for nearly 4 months now, so most of the work you're going to see, in fact, I think almost all the work you're going to see is from my time at Bristol and a little bit from my Marie Curie Fellowship, which started in 2018. So as always with me with the title, I'm kind of over-promising and under-delivering for this. I'm going to go through a lot of things, probably trying to fit as much in as possible in the time that I've got. And just give you a really good idea of, or hopefully a really good idea of what we've been up to over the last decade or so in terms of research on the Greenland Ice Sheet and trying to ascertain how important the ice sheet is for elemental cycling. So as always, there's lots and lots of people to thank for the research that you're about to see, or some of the data that you're about to see. The main people really are Gemma Wadham, Martin Tranter, Leanna Benning, and Rob Bracewell, who got me into this bun fight. Gemma Wadham and Martin Tranter are my PhD supervisors and my postdoctoral supervisors at the University of Bristol. I'm really driving a lot of the ideas behind the early development of this work. Leanna Benning and Rob Bracewell are amazing collaborators and have been very good mentors to me over the years. Lots of other fantastic collaborators, too many to name. Hopefully I haven't missed anyone out, and also students who have been, the real brains behind a lot of this research, collecting data, interpreting that data. And also just a quick shout out to the funders of most of this work, which is NERC in the UK and the European Commission for funding my postdoctoral fellowship that kept me going for the last 3 years. So the menu for today is really going through some case studies of what we've been looking at in Greenland Ice Sheet meltwaters. I'm going to start by talking about why we're interested in glaciated regions, in particular the Greenland Ice Sheet. What glacial biogeochemistry is a very young discipline. It hasn't been around for that long. The links between elements and life. And I'm going to go on to the nitrogen cycle and talk a little bit about some work we've been doing, trying to ascertain how important ice sheet processes are in the nitrogen cycle in Greenland. Then we're going to go into phosphorus. There's a lot to get in, as you can already tell, probably, and discuss whether the Greenland Ice Sheet might be a hotspot of phosphorus mobilization in the Arctic. And I'm going to go on to my favorite element, iron. I love talking about iron, and I think it's particularly interesting when it comes to ice sheets and iron sources from beneath the ice sheets. And then finish with silicon, and hopefully I won't have to rush too much through silicon, because it's also a very interesting story. The whole thing tying us through together is obviously the ice sheet mobilization, cycling, and export of elements downstream. So this first image really gives us a good excuse to talk about global warming, climate change, how much carbon we're injecting into our atmosphere, and what effect that's having on global temperatures. CO2 levels at the moment have not been this high since the Pliocene, which is around 3 million years ago, where sea levels were 40 meters higher. It's a very different world. And 2022, just 2 years ago, was the hottest year on record. And we're currently about 1 degree warmer than pre-industrial levels. It's obviously having big impacts throughout the world, none more so arguably than the polar regions, which are warming at more than twice the rate of the rest of the global average, particularly the Arctic. As you can see from this, really hot spots of global warming and increasing temperatures are the Arctic regions. Of all Earth systems, the cryosphere responds quite quickly to changes in temperature and is particularly vulnerable. And obviously a lot of the cryosphere is located in the polar regions. So this is obviously of concern, both now and going forward into the next 100 years or so, when we're expecting even more rapid changes. So what does this warming temperature mean for the world's ice? You've probably all seen these kinds of diagrams before. Sea level rise, ice sheets and glaciers are key contributors to sea level rise. Going back over the last 20 years or so, most of the sea level rise we're seeing is from glacial meltwater inputs. So this is land ice inputs into the ocean. There's also thermal expansion. This is only going to accelerate in the next 100 years or so. I've given you some context on the left-hand side here of 3 kind of major ice bodies that I've gathered into these different sections. Other glaciers basically refers to all valley glaciers, i.e. non-ice sheet glaciers. Then we've got the mighty ice sheets that cover nearly 10% of land surface area. The freshwater inputs from melting ice are really high. About 4,000 kilometers cubed of freshwater per annum per year is coming from glaciers. It's about 15% of global riverine discharge. I've also partitioned this into iceberg inputs, so solid ice discharge and runoff, so it's meltwater discharge. And it differs a little bit depending on what kind of system you're looking at. The Antarctic ice sheet is mostly iceberg discharge at the moment. It probably will be for hundreds of years, whereas the Greenland Ice Sheet is about 50-50 iceberg runoff discharge. And runoff is actually increasing considerably over the last decade and probably forward into the future. And I think some of these contemporary processes, understanding some of these contemporary biogeochemical processes and sedimentary processes, geomorphological processes, are also obviously really important for trying to understand past environments. And just 21,000, 22,000 years ago, these great ice sheets covered a lot of North America and a lot of Northern Europe, the Eurasian ice sheet over Europe and the Laurentide and Cordilleran ice sheet over North America. And also, large ice sheets over Patagonia and Iceland as well. So trying to understand and trying to get a better idea of what's going on in the present day with ice sheet biogeochemical processes might give us a really nice insight into past impacts of glaciations. So I'm sure there's glaciologists on this call, on this Zoom, and probably other people as well. I don't have to tell you this, but there's water at the bed of ice sheets and at the bed of glaciers at the ice rock interface. In fact, the more we look, the more water we seem to find at the bed of ice sheets and glaciers. And this has all kinds of implications for biogeochemical processes and also physical processes by, for example, lubricating the ice rock interface and allowing ice to flow faster. It's a little bit of a different story depending on where you look. In Antarctica, for example, a lot of the subglacial water is rather isolated and fixed into these subglacial lake systems. More than 650 subglacial lakes have now been identified under Antarctica, and these sit at the ice rock interface there. And they're broadly categorized into active subglacial lakes and isolated subglacial lakes. The active ones on this map are shown by these triangles. The isolated ones are shown by the circles. And the active ones fill and drain on kind of periodic cycles. So they're connected to each other and also to the marine environment downstream. In Greenland, again, as I said, the more we look, the more water we seem to find in Greenland. This just gives an idea of the Greenland ice sheet and the environments beneath the Greenland ice sheet, which are lightly thawed, i.e. there is water at the bed, and the environments which are lightly frozen, i.e. the ice is likely attached to the bedrock and there's likely not any liquid water. Saying that, the more measurements we take, the more we seem to find liquid water, even in environments where we don't expect it. And that might be at the bottom of some of these ice cores that are being taken, like NGRIP, and it might be through geophysical surveys, increasing the amount of geophysical surveys that are being done. And so now I'm basically going to focus on Greenland from now on in. So this schematic is an idealized schematic of the Greenland Ice Sheet outlet glacier. This is actually a land terminating glacier, and the system that I'm going to present almost all the data today from. This is what it looks like when you cut open a land terminating catchment of the Greenland Ice Sheet. As you can see, it's a very complex hydrological system that evolves over a meltwater season. So the meltwater season is approximately from April to September. This is when ice melt is occurring at the ice surface. And this progresses inland as you remove snow cover that was deposited over the winter, and you produce these really active surface hydrological environments. Active weathering crusts, a living skin. There's microbes living on the surface of the ice, and they're very active in places. And you also open up these drainage pathways from the surface of the ice down to the bottom of the ice, the subglacial environment. So linking the subglacial and the superglacial environment occurs during the melt season. Over the course of the melt season, this ice sheet hydrological system expands inland underneath the ice sheet. It becomes more efficient. The more water you throw down into the base of the ice sheet, the more efficient the drainage pathways become. And that's really important for some of the biogeochemical processes that we're seeing. Also, as you go further inland, as you start draining waters further inland underneath the ice, you start draining more isolated waters that potentially have been stored under the ice for at least a year or potentially several years, and are actually poorly connected to some of the drainage pathways and act a little bit more like groundwater. So we have these surface processes going on where you're generating large quantities of ice melt during the summer, increasingly larger quantities of ice melt during the summer as it gets warmer. This is an example of a superglacial lake. These lakes can be several kilometers in diameter and can drain incredibly rapidly through the ice as they actually hydrofracture the ice beneath them and drain very rapidly to the subglacial environment. And they perturb the subglacial hydrological system when they do that. Then you have these large moulins, pipes in the ice, and crevasses that drain the surface water into the bed of the ice sheet. And that's where you get a lot of biogeochemical reactions going on, as I'll talk about in a little bit. Isolated waters, plus these surface waters mixed in, plus some sediments mixed in, makes for a really interesting environment. And then that water comes out the front of the ice. This is an example of quite a nicely constrained meltwater portal at Leverett Glacier, which is the glacier that I'm going to be talking about during this talk. This meltwater exits the glacier, extremely turbid, grams of sediment per liter of the meltwater. That gives it this milky color. And this is mainly actually surface meltwater that's been mixed in with sediments and a little bit of stored waters underneath the ice. But it looks very different to what it looks like on the surface because of this really high sediment concentration. This is a nice video taken by some of my colleagues at the University of Edinburgh of a meltwater river in southwest Greenland. This is Leverett Glacier meltwater river around June time. It gives you some idea of these incredibly rapid changes that occur in this river over relatively short periods of time. There's a rhodamine dye trace going on there. My colleague Andrew Tedstone. And then these meltwater rivers can get extremely big in peak melt. This gives you an idea of what it looks like in July. At this point, there's probably about 400 meters cubed of water going through this river. This is at the end of July in 2012. This was a record meltwater event from our records anyway. And at this point, the river is about 800 meters cubed per second in discharge. And this is actually probably not considered a large meltwater river for Greenland. This is a medium-sized meltwater river in Greenland. And then this meltwater gets to the marine interface and flows out as these buoyant sediment plumes that you can actually see from satellite images. About a third of all Greenland's glaciers are marine terminating glaciers, and that means the ice terminates in the marine environment or in fjords, and that's demonstrated by the schematic below. And these act quite differently actually to land terminating systems. Biogeochemically, they're very important because the meltwater exits at depth in the fjord or the marine environment, can be tens to hundreds of meters at depth. And it's a buoyant, fresh sediment plume. And what it does is it upwells near the ice carving front, and it brings with it marine waters from depth, which tend to be quite high in nutrients. So these systems are actually really, really important for generating elevated nutrient concentrations at the surface of fjords because of this meltwater pumping system. And again, this is a quick video to show you some kind of idea of what the meltwater drainage system is looking like at peak flow. You have these surface meltwaters going into the base of the ice sheet, draining along that ice rock margin, potentially as these subglacial rivers that we can't see, exiting the front of the ice sheets at depth, and creating these buoyant, turbid plumes that entrain deep marine waters and bring them to near the surface of fjords and marine environments. So a lot of this work that we've been doing over the last 10 years and that others have been doing over the last decade or so in Greenland is really motivated by the incredible developments in our field of glacial biogeochemistry over the last 20 to 30 years, really big step changes, big paradigm shifts in the way we understand glacial systems as biogeochemical reactors. This gives you an idea of, just 2013, not even 10 years ago, textbooks coming out that have ice sheets as blank spots on the map of both sediment and dissolved solid discharge into the oceans. And we think this is an issue. There's reasons they have been left blank. It's difficult to get data here. These environments were thought to be frozen, inhospitable, devoid of life. We now know that's very, very much not the case. And people are now starting to add numbers to these kinds of systems. And that's kind of part of our motivation here, is to contextualize these ice sheet systems within the Earth system as a whole. So this gives you an idea of the fluvial sediment export to the coastal oceans every year. So again, this is from Milliman and Farnsworth. And even fairly recently, 2017, we managed to start putting numbers on the Greenland Ice Sheet for sediment export to the ocean. This is Irina Overeem's work. And these numbers are very, very high, actually. It's sediment export from the ice sheet to the ocean, Greenland Ice Sheet to the ocean, is 5 to 10% of the global sediment export to the ocean. That's what the estimates suggest anyway, despite just covering 1% of land surface area. So these are hotspots of change and hotspots of sediment export and potentially hotspots of biogeochemical weathering. So this schematic is my poor attempt to try and explain glacial biogeochemistry in one slide. What we basically have here is a glacier flowing downstream, glacier flow this way, surface inputs to the bed, water at the bed. This glacier is like a big bulldozer. Glaciers are the bulldozers of the natural environment, both now and in the past. What this does is it crushes the bedrock beneath it, acts like this big boulders, it crushes the bedrock beneath it. All these trace reactive components in that bedrock are suddenly exposed to liquid water and ground to very fine, very fine sediment sizes, silt and clay sized particles. These particles weathered by microbially catalyzed chemical weathering underneath the ice. And also we get this formation of all these nanoparticles and amorphous nanosurface environments on these particles as they weather in these environments. That's basically all you need to know for now, I think. And it's difficult interpreting some of these processes, this glacial biogeochemical weathering, because most of the time we're taking samples at the front of the ice, at the front of the glacier. But really, that sample is an integrated signal of everything that's going on upstream, which includes water coming from the bed, stored water at the bed, which has high dissolved solids, long residence times, is possibly anoxic. There's a lot of evidence to suggest there's anoxic meltwaters underneath the Greenland Ice Sheet, for example, and also underneath the Antarctic Ice Sheet. It's also the combination of basal meltwater, so the base of the ice itself melting, and also the combination of surface meltwater. Actually, this is where most of the meltwater that comes out the front of the ice, comes from that surface environment, where we have very low dissolved solids, because mainly ice melt and snow melt, very short residence time sometimes, particularly in peak discharge. And that water is super saturated with oxygen. Combine that with these physical erosion products, this really finely ground sediment with reactive surface layers, and you get some kind of signal at the front, this subglacial meltwater discharge that comes out the front that we now got to interpret. So it's a complex environment. So much of our work over the last 10 years has been focused on bioessential elements and how important ice sheets might be in mobilizing some of these elements and cycling some of these elements for export downstream. So both freshwater systems, freshwater ecosystems, but also potentially marine ecosystems, coastal ecosystems. Biomass contains about 30 different elements, and all organisms must obtain chemical forms of most of these elements in order to survive and thrive, some of them in very small quantities, like ones we term micronutrients, and iron is one of those, one that we're going to focus on today, one of our case studies. But also macro elements, macronutrients, major essential elements for all life. Examples of those are nitrogen and phosphorus, which we're going to talk about today, and also silicon for some types of life. For example, marine diatoms that build their cell walls out of opal, which is silicon. And there's also this motivation to investigate how important meltwaters might be in carrying nutrients because of the impacts on marine ecosystems, like I've already suggested. These are chlorophyll concentrations in the ocean. Half the oxygen we breathe, or approximately half the oxygen we breathe in the air, comes from the ocean, from marine ecosystems. The plants of the ocean, phytoplankton. And they only comprise about 1% of plant biomass on the planet, yet they're responsible for about 50% of global primary production. These guys also drive the marine ecosystem, the marine food web, and they're responsible for the productive fisheries where we get a lot of our fish from, things like shrimp, halibut, mackerel from Greenland. There's lots of productive fisheries around Greenland, and in fact, fisheries account for, I think it's over 90% of Greenland cash export. So incredibly important processes occurring at these coastal margins where you get high productivity. And so trying to ascertain how important ice melt might be and how that might change in the future is obviously what we think are quite important. There's a couple of different ways in which glaciers can transport elements to ocean surface environments where they might be utilized by marine phytoplankton. I've kind of grouped these into direct and indirect ways. The indirect ways I'm not going to talk about, so I'm not really going to talk about the marine ecosystem and glacial meltwater mixing into the marine ecosystem during this talk. There are people far better qualified to talk about that than me. People like Lorenz Meyer have been working for a number of years on the coastal environments around Greenland, and they have a much better grasp of what's going on there. So I'm talking about meltwaters here, the flux at the gate. Mainly, most of this talk is focused on the flux at the gate, and what I mean by that is the flux when the meltwater exits the glacier. rather than the flux when the meltwater mixes into the marine environment, and all kinds of complex processes are going on there that I don't have time to talk about, and other people can talk about that a little bit better than I can. So the indirect ways in which nutrients might get into the marine environment are things like this ocean water entrainment that I was talking about, this deep water pumping of deep marine waters rich in nutrients like nitrogen and phosphorus from this upwelling subglacial discharge from marine terminating glaciers. So that's kind of an indirect input. It's not coming from the glacier, but it is being upwelled by glacial physical processes. Then there's also benthic recycling. A lot of work has been done on this in places like Svalbard by folk like Laura Verman. This is a schematic from her 2014 paper. And this is basically looking at those reactive glacial sediments as they're deposited at the bottom of fjords, and they're processed, diagenetic processing. And this can actually release a lot of important nutrients to the overlying water column, things like iron and manganese, for example. As I said, I'm going to focus on these direct inputs, not so much the icebergs, the meltwaters. So the Greenland Ice Sheet, as I've already alluded to, is a really interesting system. It exports a large amount of fresh water to the Arctic every year. It covers about 20% of the Arctic land surface, so it's a big component of the Arctic. And together with icebergs and meltwater, it's about 1,000 kilometers cubed of fresh water export to the oceans every year. Obviously, a lot of that gets into the North Atlantic Ocean as well. And it's really high amount of sediment export, which has been identified in the last 5 or 10 years or so. The earliest reference I know to this is some of my collaborators in University of Edinburgh who actually started quantifying erosion rates beneath the Greenland Ice Sheet based on the glacial catchment that we're going to look at today. And that's Tom Cowton and Pete Nino and his colleagues at the University of Edinburgh have done a lot of that work. So this is the field site that I'm going to talk about through the rest of this presentation. This is Leverett Glacier in southwest Greenland. It's where we've done the majority of our work. It's a catchment that we think we understand quite well now. Some fast facts about this catchment: it's about 600 to 900 kilometers squared in size. It goes about 50 kilometers into the ice sheet. It exports about 2 kilometers cubed of meltwater a year, just in this one little river that comes out the front. So little can be quite a big river. And it's underlain by Precambrian gneiss and granite bedrock, which is broadly representative of most of southwest Greenland, at least, and a large majority of other parts of Greenland. So it's a good place. We think it's a good place to go and try and understand ice sheet processes and contextualize them within the kind of Greenlandic viewpoint. And the data I'm going to show, as I've mentioned already, is data from the front of the ice collected near the glacial portal when it comes out of the ice. This turbid meltwater comes out of the ice, and also some data from the surface of the ice, just to show you the difference in these two end members, and just to infer as well where most of our nutrients or most of our elements are coming from in this system. And you're also going to see a few of these today, these hydrographs. This gives you an idea of the discharge over a melt season at Leverett Glacier. I've just chosen here 2009 to 2012, where we have continuous records of discharge, and separated them roughly into June, July, August. May, June time, spring, early summer is where the discharge starts ramping up very quickly, in fact, from a little trickle of a stream in May to a decent sized rivers in mid-June. July, where you usually get peak melt at Leverett Glacier anyway, anywhere between 200 and 800 meters cubed per second. And August, where meltwater discharge is still high, but it's starting to decline a little bit. To give you a very quick, very brief explanation of the right-hand side here, this is electrical conductivity, which is a decent proxy for total dissolved solid concentration. Over the melt season, there's this very general trend of declining electrical conductivity. As you ramp up the amount of melt, electrical conductivity goes down, and that means your waters are getting more dilute over the melt season. There's obviously a lot of intricacies with this. There are some blips, and I will explain some of those a little bit later. Grab a sip of tea, very important. So I'm going to start by talking about nitrogen and nitrogen concentrations and fluxes from the Greenland Ice Sheet. So I'm not going to talk through all of these nitrogen cycle diagrams. I just wanted to show you how intricate nitrogen cycle is, how important it is for biology. The global nitrogen cycle is central to the biogeochemistry of the Earth. Large natural flows of nitrogen from terrestrial and marine ecosystems occur, and between terrestrial and marine ecosystems. And nitrogen is used to produce things like amino acids, nucleic acids, proteins, other cellular components, really important component of chlorophyll, for example. And it's thought to be the key limiting nutrient in a lot of the Arctic, and particularly in the fjords around the Greenland Ice Sheet. So you add more nitrogen, you can potentially stimulate more prime production in these environments. In this particular study, we were looking at two kind of sets of data. One was data collected from superglacial sampling site, about 40 kilometers, 30, 40 kilometers onto the Greenland Ice Sheet. This absolute hero here, Dave Chandler, actually camped at this site for 3 months in the summer of 2012 and collected a lot of the superglacial samples. So we do have a seasonal record in superglacial nitrogen speciation and concentration. And then for the rest of us folk, we were sat here at the front of the ice for about 3 months, taking samples from this subglacial meltwater that was exiting Leverett Glacier here. And this is what our time series looks like over that time period. I want to draw your eyes down here. This is our inorganic nitrogen species, ammonium and nitrate. As you can see, there's a general decline in nitrate over the melt season from more concentrated values in early season when the meltwater input is, or the meltwater discharge is much lower. This is discharge up here. And as the meltwater discharge goes up, our nitrate concentrations decline. And these are actually pretty low concentrations of dissolved inorganic nitrogen. They start around 4 or 5 micromolar, and they get down to limits that are near detection or around 1 micromolar. This is very, very low, and indicates actually that glacial meltwaters are pretty dilute in terms of nitrogen species. It's also the case for dissolved organic nitrogen. There was actually more dissolved organic nitrogen in these meltwaters than we anticipated, but it was always around 4 to 2 micromolar or a little bit less. A large proportion of this nitrogen is thought to be from surface environments based on those measurements that poor Dave Chandler, who's camped there for 3 months, took from his little field camp there for 3 months. We know that nitrogen is deposited from the atmosphere onto the ice sheet surface, and it's likely this atmospheric nitrogen is swept into the subglacial system. Saying that, we have samples taken at the Moulin, where Dave Chandler was camped on the ice sheet, and from the runoff in front of the ice sheet, taken at the same time. And these seem to indicate an enrichment in total dissolved nitrogen as you go from surface to subglacial environments. So there's some assimilation of nitrogen in the subglacial environment, and we're still a little bit unsure where that comes from. It could be coming from a little bit from the bedrock, for example, nitrogen in rock, but it's still to be ascertained. So there's our low dissolved organic nitrogen concentrations, particularly at high discharge. And that's mainly ice melt, dilute ice melt, that's driving this low concentration. There's our total dissolved nitrogen concentrations. Significant proportion of the nitrogen seems to be coming from the ice sheet surface, from this atmospheric deposition. And when you wave your hands around a little bit and you try and calculate fluxes of dissolved organic nitrogen from the ice sheet based on this one catchment, lots of caveats, it's of a similar order of magnitude to an Arctic river, about 40 gigagrams per year. So that surface environment is really biogeochemically reactive. This is some work from Alexandra Holland. I'm not actually involved in this work. This is work from some of my colleagues, but I thought it was particularly interesting to include because the surface environment can retain very, very high concentrations of nitrogen. On the graph to the right here, L, M, and H indicate ice environments with low, medium, and high impurity concentrations, and these impurities are mainly algal cells, actually, ice algae cells. And within these environments, you can actually get extremely high concentrations of dissolved organic nitrogen. And that's thought to be related to these ecosystems retaining that nitrogen and cycling it within these ecosystems. Interestingly, then, when you look at the surface meltwater streams, the meltwater that gets into the ice bed environment, the concentrations are extremely low. So this surface weathering environment, the surface weathering crust, very biologically active, and the ecosystems, you know, at holes likely produce and retain these nitrogen compounds on the surface rather than allowing them to drain into the ice sheet and out the front. We also have these really cool sensor records. This is data from Alexander Beaton, from our collaborators at the National Oceanography Center, and he's been part of a team developing these lab-on-chip sensors, these colorimetric nutrient sensors that can be placed in situ. An example of the deployment we had at Leverett Glacier in 2015, and this is what these sensors look like. And this is able to generate very high resolution nitrate measurements, where you can start observing diurnal variations in nitrate concentrations and start linking those to biogeochemical cycling of the nitrate. And it appears that a lot of the nitrate in the meltwater stream at this part of the season, which is early season, seems to be coming from groundwater. So our peaks in nitrate concentrations actually are about the same time as you have peaks in EC, electrical conductivity, and low points in discharge. So these kinds of sensors, I think, are really, you know, an integral part of future biogeochemical monitoring, and they prove that by taking very high resolution samples, you can start to tease out quite intricate cycling processes you can't get by taking spot samples or just one sample a day. So next, I'm going to move on to phosphorus cycling and try and answer the question of whether the ice sheet, the Greenland Ice Sheet, is a hotspot of phosphorus mobilization. It's one of our big meltwater rivers again. Again, very briefly, like the nitrogen cycle, I'm going to very quickly talk about the phosphorus cycle, which could be an entire talk. But phosphorus, like nitrogen, is an essential macronutrient needed in quite high quantities by biota, which is interesting because it's actually a very rare element. Life scavenges phosphorus. It's usually available in very low concentrations. In the Earth's crust, the major source of phosphorus is apatite, this mineral here, it's phosphorus-bound mineral here. And that's actually at pretty low concentrations in the Earth's crust as well, and is fairly insoluble. Phosphorus is essential in biochemical processes. I've already mentioned, it's often thought of as the staff of life, backbone in cell RNA and DNA, and it's also used in cell metabolism and in processes like generating ATP synthase and structural molecules like phospholipids. So that's why we're interested in measuring phosphorus in all kinds of freshwater systems. This is our time series data, dissolved phosphorus from Leverett Glacier, that same glacier, as I showed the nitrogen concentrations. Something quite interesting going on here in terms of the cycling and mobilization of phosphorus. I'm going to focus you in on SRP, which is dissolved inorganic phosphorus, soluble reactive phosphorus, that stands for. And these SRP values seem to be hydrochemically controlled, very strong temporal dynamics, starting from quite low concentrations in the early meltwater season, and these pulses of high concentrations coming through the subglacial environment at certain parts of the season. Interestingly, and almost conversely to what you would expect, the highest concentrations of dissolved phosphorus actually occur at peak discharge at Leverett Glacier. And that's, you know, the opposite of what we would expect looking at the electrical conductivity record. And there's all kinds of reasons behind this. And we think this is mainly driven by the very high pH values in these late season meltwaters. The pH of the meltwaters can get above 9.5 at certain times in the melt season. And that's really great for dissolving phosphorus or releasing phosphorus from where it's bound up, which can be in things like iron oxide, hydroxide minerals. Almost all this phosphorus is coming from the subglacial environment, very, very little phosphorus in the superglacial environment, and most of that seems to be retained as well. But high concentrations, or relatively high, environmentally high, I should say, these are not high concentrations still, are found in these meltwaters exported from beneath the ice sheet. So we're generating all this dissolved phosphorus from subglacial processing of probably phosphorus-rich rock. That's also reflected in these particular phosphorus concentrations, which seems to be indicative of freshly crushed rock. No surprise there. I want to draw you down to these highly reactive components: magnesium chloride, extractable phosphorus, sodium hydroxide, extractable phosphorus. And these guys are usually termed the highly reactive components. And they seem to be correlated to the dynamics we're seeing in the dissolved inorganic phosphorus concentrations in the river. And to us, this is suggesting there's some kind of significant buffering of dissolved inorganic phosphorus by particular phases, and most likely iron and possibly aluminium oxyhydroxides. And that there's also temporal variations in these particular phases as well. as the geochemical characteristics of the meltwater changes, as the pH of the meltwater changes as well. This may also indicate that phosphorus phases are quite easily cycled between these particulate phases and the dissolved phase. And that might indicate that these phosphorus fractions are labile on relatively short timescales in glacial environments like Leverett Glacier. So again, if you do some hand waving, you try and figure out yields of phosphorus from the ice sheet based on the data from Leverett Glacier, and also we have some data from another glacier in southern Greenland, but mainly based on the data from Leverett Glacier, you actually start to tease out some pretty significant numbers. So when you normalize catchment soluble reactive phosphorus yields by area of the catchment, you get quite significant values, up to 25, 26, 27 kilograms of phosphorus per kilometer squared per year, coming out of the Greenland Ice Sheet at some of these marginal glaciers. I've just put some context in here of other big riverine systems and glacial systems, and you can see that these are very substantial soluble reactive phosphorus yields, so dissolved in organic phosphorus yields that are coming out of the Greenland Ice Sheet. Particularly considering that this ice sheet system hydrologically is only seeming to be active and certainly only exporting this phosphorus for a limited number of months per year. And then this is where a little bit more controversy comes into play. If you look at total phosphorus yield, so this includes all the particulate phosphorus as well, then really these glacial catchments come into their own because of this very high sediment yield from ice sheet catchments and from other glacial catchments. So the ice sheet clearly mobilizes a lot of phosphorus, mobilizes it from the bedrock and exports it to downstream environments. But a lot of this phosphorus is this finely crushed ground apatite mineral, and that seems to be fairly insoluble in a marine environment. And indeed, when you look at downstream fjord environments, you don't see a phosphorus signal from this, in terms of dissolved phosphorus signal, from this particular phosphorus phase, which probably indicates that a lot of this phosphorus that is mobilized from the ice sheet is being buried in the near coastal environments. So going on to iron now, iron hypothesis that many of you probably heard about was really kind of started by an oceanographer guy, Jon Martin, and he identified that iron is a limiting nutrient in a lot of marine ecosystems. It's a micronutrient needed in very small concentrations, but still essential to marine phytoplankton. And where it's lacking, it can actually reduce the growth of this marine phytoplankton, can limit the growth of the marine phytoplankton. Main locations where that's occurring are mostly around the Southern Ocean, also in Alaska, in the Gulf of Alaska. Jon Martin seems like he was very much a character. He's semi-famous for standing up at Woods Hole seminar and saying something like, "Give me half a tanker of iron and I'll give you the next ice age." He was very interested in this glacial interglacial CO2 change due to differences in iron fluxes to the ocean. So where does iron come from in Greenland? Certainly not coming from the ice sheet surface. Ice sheet surface, very important for driving hydrological changes. Here's our hydrograph again. These shaded areas are what we call meltwater pulse events or outburst events. And these are events that occur due to very rapid drainage of surface meltwaters into the subglacial system and perturbing that system. Really important for driving subglacial hydrology, not important for dissolved iron concentrations. This is the log scale. This is superglacial meltwater versus Leverett Glacier outflow. I just want you to concentrate on the blue bar here. Concentrations in Leverett Glacier outflow of dissolved iron are over 1,000 nanomolar. In the surface environment, they're under 10 nanomolar or around 10 nanomolar. So orders of magnitude difference between the surface and the bed. All down to this subglacial reactor, a bit like the phosphorus cycle as well, where you have this bedrock comminution, high rock water ratios, redox gradients, microbes that we know can cycle iron, and some circumstantial evidence to suggest you can generate high iron concentrations in these subglacial environments. This is Taylor Glacier in Antarctica, Blood Falls. These are ferrous-rich brines that drained into the Engrip borehole when it was drilled and were extracted. And again, some kind of temporal variation and very high iron concentrations maintained almost throughout the whole melt season at Leverett Glacier. Next, we're going to look at the particulate phase. similar kind of story, very high values of ascorbate extractable iron, and ascorbate extractable iron includes amorphous iron nanoparticles that we know are at least partially available to marine biota or biota in general. They're highly reactive, have very high surface areas, very small. This is what they look like under a scanning electron microscope. These aggregated microparticles, like little globules, and we know they are, to at least some extent, bioavailable to marine biota. And we've characterized these nanoparticles also to look at the iron speciation. Very quickly, iron speciation is also thought to be quite important in dictating iron bioavailability. And what we find in these aggregated nanoparticles is high concentrations of iron 2+, which is thought to be more biolabile than iron 3+. A mean of about 40% iron 2 content in identified nanoparticular aggregates in this work that we did. And this is based on synchrotron methods, synchrotron-based radiation methods, more specifically scanning X-ray microscopy. And just to give a shout out to some others that have been working on this iron question in the terrestrial environment in Greenland. If you're interested, please do go and look at some of these other papers. They do a really nice job at trying to quantify the amount of iron in glacial meltwaters. As you can tell, I'm trying to speed up a little bit here. We're on to our final case study, which is silicon export from the Greenland Ice Sheet. And I promise this is the final one we're going to look at. Silicon's important because it's an integral component of marine diatoms, and marine diatoms build their cell walls, their shells, frustrals, out of silicon. And these guys account for 30 to 70% of ocean prime production. I think this is more likely 40% of ocean prime production, but a significant component. And they have an absolute demand for dissolved silicon. The weathering of silicate minerals also consumes atmospheric CO2. This is the carbonate silicate cycle, and it's thought to help control CO2 concentrations in the atmosphere over geological time periods. And there's interesting dynamics when it comes to silicon in Greenland Ice Sheet meltwaters. This is from some work we published a few years ago. Dissolved silicon, often near detection in the surface meltwaters, much like iron. So all of this silicon is coming from the subglacial environment, that interaction of water and freshly ground bedrock. There's a seasonal dilution in dissolved silicon from around 60 micromolar at early season meltwaters to around 20 micromolar at peak flow. We also get these very high concentrations of this extractable amorphous silica, which you think is at least partially reactive, and we know dissolves at least a little bit in the marine environment, on which timescales we can debate, but it dissolves in seawater. And that's usually very high concentrations because of that very high concentration of suspended particulate matter, which is over here, often over 1 gram per liter during peak melt. And we also get these large variations in silicon isotopes, reflecting changes in subglacial weathering pathways as the melt season progresses. I'm happy to talk separately about that later if people have questions about the silicon isotope record, but I'm not going to talk about it now. It's an additional bit of complexity. So again, if we wave our arms around a little bit and come up with some numbers, the export of silicon from the Greenland Ice Sheet could be quite considerable. But, and the big but is, almost all of that silicon is contained in that amorphous silicon phase that I was just talking about, extractable from the suspended sediments. And we know it's there, we've extracted it, we've also characterized it under electron microscopy. This stuff can be very high in silicon, but it could also incorporate other elements like aluminium, which could change the way it reacts in the marine environment. We've also added some of these suspended sediments to marine waters, low dissolved silicon marine waters, and we've seen this amorphous silica dissolve in those waters over time. Over a period of days to weeks, that stuff starts to come off, and over a period of a month, it seems like about 20% of the dissolved silica, the amorphous silica, can dissolve in marine waters in these idealized conditions in a lab, obviously. So its fate in coastal environments seems less certain, probably due to the very short residence time to the sediment in the water column. And I think still to be determined the fate of this amorphous silica, particularly in marine sediments where a lot of this stuff is deposited. So I've come up with this idea of kind of trickle, well, not me, me and others have come up with this idea of trickle and treat when it comes to glacial meltwater inputs of elements into the ocean. And this is based on this diagram, really. There's two main inputs of glacial nutrients. There's this indirect subglacial meltwater pumping, which is really the treat for things like nitrate and phosphate, soluble reactive phosphorus. And then there's this turbid meltwater discharge at the grounding line, which we've shown to contain very high concentrations of iron, potentially significant concentrations of silicon, even dissolved silicon. There's enough dissolved silicon in there to provide silicon to surface meltwaters and fjords, and also reactive particles. So the balance between these two is almost certainly controlled by the subglacial meltwater pumping of these deep marine waters, bringing nitrate and phosphate to the surface of the fjords. That seems to be the most important process in dictating the productivity of these fjords, because these fjords around Greenland are nitrate limited, or seem to be nitrate limited. So that's it. I'm sorry I had to go through those quite quickly. I just wanted to give you a quick summary, some concluding remarks. I'm just going to leave these on the screen. Happy to take questions. And thank you very much for tuning in and listening.
Hey, John, that's a great talk. Thank you so much. Let's see if the audience, if you have any question, go ahead to unmute yourself and ask John. Anybody? Hey, John, I have, it's so amazing to see that so much phosphate come down. So the question is, anybody report the near shore, the water, the primary production, the algal bloom? Because on ice, on snow, the algae bloom reported many. But how about this discharge export to the coastal water, to the food even?
Yeah, absolutely. So this is work that's been done by people like Lorenz Muir at the Greenland Institute of Natural Resources and people like Mark Hopwood. And there's quite a bit of data on chlorophyll concentrations in Greenlandic fjords, especially in southwest Greenland. And this is where some of the controversy comes in, actually, this disconnect between the meltwater inputs and the cycling of these nutrients in these marine ecosystems. So it seems like surface waters in fjords are primarily nitrate limited, but there's also very low concentrations of phosphate. Mm-hmm. And even though there is quite a lot of phosphate coming out of the ice sheet, most of it is in this particulate bound form, the soluble reactive phosphorus concentrations coming out of the ice sheet aren't enough really to perturb some of these concentrations of phosphate in the fjord. And a lot of that phosphate in the fjord seems to be coming from deep water pumping of marine waters, bringing that to the surface. And you can get very high concentrations of chlorophyll and a lot of primary production in these fjords. They're pretty active ecosystems, but a lot of that is thought to be fed actually by this deep water pumping of nutrients rather than the direct input of phosphate or nitrogen from glacial meltwaters. There's also this discussion about, glacial meltwaters have so much sediment in that when they're introduced into fjords, they can actually limit primary production because these fjords become light limited, as well as nitrate limited or nitrogen limited. So there's still a lot of work to be done, I think, but there's been a lot of work done over the last 5 years that have tried to look at some of these coastal processes, or that are looking at these coastal processes.
Yeah, that's very interesting, particularly because in other systems, we see the very turbid water environment. After we pass that turbid water distribution limitation, the nutrients still high. That's the zone for the primary production is boom up.
Yeah, exactly. And that's exactly what happens in these marine terminating glacial systems. So you get this upwelling bloom, this upwelling plume, and that brings with it those marine waters and also the micronutrients in glacial meltwaters. Another interface between the turbidity and the less turbid surface zone, that's where you get all the primary production.
Exactly. Okay. Anybody else?
Hi, Jon. May I ask a question here?
Go ahead. Yeah. Xiaole.
Thanks for the high peak phosphate flux when the pH was high. So do you see like a correlation between the phosphate and the silicon flux? I mean, if you have a high pH, we would also expect there's a high silicon free from iron oxides or weathering process. So do you see like there's any correlations between them?
Yeah, it's interesting actually. There is no correlation or like very weak correlations between phosphate and silicate. So dissolved inorganic phosphorus and dissolved silicon. Very little correlation between the two. So the reason why we think that the phosphate is controlled by the pH is that there is a very noticeable increase in soluble reactive phosphorus when you hit a pH of 9. Point of zero charge for iron oxide hydroxides changes, and we think all this phosphate is coming off those iron oxide hydroxides and into solution when you have those high pH pH levels. Doesn't seem to be the case for silicon. When you have high pH, it seems to weather aluminosilicates. I didn't show this data, but we have high concentrations of aluminum, for example, dissolved aluminum, or aluminium, I should say, British version I should use. High concentrations of aluminium, but not of silicon. So we think the silicon is retained in that weathering crust on the particle as this kind of amorphous mineral, this amorphous silicon mineral, and not released into the meltwater. So it's kind of like this depleted surface crust, a surface weathering crust on the sediments rather than in the water itself.
Okay, so maybe, which means like such a large of amorphous silicon, maybe they are not available as a nutrient for the coastal system, if that's the case, right? Yeah,
I think not directly available, certainly. We know that if you add these sediments to a low silicon marine water in the lab, this silicon dissolves. Because we can see that dissolving in the lab, and 20% of it dissolves in over a month. That's probably not, that's rapid dissolution in terms of geochemistry, but it's probably not rapid enough to be able to observe that in the marine systems. And as a lot of this sediment is removed from the water column fairly rapidly, it's probable that this amorphous silicon is deposited in the marine environment, in the sediments in the marine environment, and not actually released. I think there's still questions to ask about diagenetic processes in the fjords and how important they might be in dissolving some of this amorphous silicon in the sediments and providing a diffusive flux of dissolved silicon to the base of the water column. But I think that's starting to be done by people like Kate Hendry, for example, who's now at British Antarctic Survey. But yeah, it doesn't seem like that immediately affects the water column when it enters the water column, the amorphous silica.
Okay, thanks a lot.
Anybody else? So John, I have another question. You compared the elemental export from Greenland to other Arctic rivers like Ober, like Yukon, Mackenzie. So of course, that's extra large, is much more. But how about compare other like a tropical river system? I just want to get a sense. I should look at the number to compare, but
we have played around with comparing to tropical river systems. We tend to stay in the Arctic with a lot of these comparisons. I can't remember off the top of my head how they compare. Certainly, when you compare it to things like the Amazon exports, a much greater proportion of some of these elements than the Greenland Ice Sheet does. And the way that these river systems export the elements is quite different as well, because you have a lot of organic matter in non-glacial rivers that binds up a lot of these elements and either enhances their export or could be less labile than some of these inorganic elements that we're seeing, or inorganic compounds that we're seeing in glacial meltwaters. So it's quite a difficult thing to do, comparing these river systems to the Greenland Ice Sheet. We have done a little bit of it, but we've mainly done that when trying to normalize the mobilization of these elements. So when we look at the tons per kilometer squared mobilization of these elements, that's when we compare them to other river systems. And when you have these very active Greenland Ice Sheet outlet glaciers, they do seem to mobilize more of that element per unit area than a lot of other river systems. That does seem to be the case, but a lot of that is diluted by these very dilute surface waters that come in, so the concentrations don't always reflect the high mobilization rates.
Okay, very good. So anybody else? Any other question? Okay, that's very interesting. You know, because when Irina Overeem came out the sediment number, it said it could be counted about 8% of the global sediment discharge. That's a really very good relevant number. You know, so for that biochemical element, we want to get a sense which role of the Greenland played in the global biochemical budget.
Absolutely. So, yeah, and that's what we've been trying to do, is to start putting some numbers on some of these elements.
Yeah.
At the meltwater end member anyway.
Yeah.
And then we can talk about and we can discuss like the processes that occur in the near shore, which is the same with sediment, right? The same, same kind of discussions are happening. But you know, we know that at that kind of like glacial boundary, the amount of elements that are being exported out of the ice sheet is pretty high. But it's mainly controlled by the sediment.
Sure.
So it's very reactive, fine sediment.
Interesting, very interesting. So if you know any other question, I think, John, thank you very much for this great talk. And also your talk is archived on our YouTube channel. So if anybody, your friend or student, you want to assign them to watch, go ahead. For the audience, you go ahead to get the link. And
thank you so much. Yeah, thanks, Paul. And thanks so much for putting on this amazing seminar series as well.
Well, thank you.
Enjoyed it a lot last year.
Yeah, looking forward to some of you next week. So thank you.
Thank you.
Yeah.
Thanks everyone.
Thomas Hoffman, you're here.